Okay, today we're going to look at linear interpolation. I'm going to skip least squares and let you read that. We'll look at logs and exponentials. Okay, so graphs of linear equations. So for many of you, this will be revision because it's a really elementary topic. So let's go over how we construct a line. So given 2 points, say 2, 1 and 3, 2, we can form the slope by just rise over run. So this part here is the rise, and in this case it's 2 minus 1, and then the run is this little part, the difference in the x coordinates, which is 3 minus 2. So our slope then is 1 over 1, which is 1. Now it's important to keep the coordinates in some particular order. So for example, you could do that the other way around, but you need to be consistent in the order. You see the same number in the subscript occurs in the left positions of the numerator and the denominator respectively, and likewise here. So you don't want to swap those. Alright, so what this gives us is the slope, but then we have from that y equals mx plus c, and the m is equal to 1. So we now have y equals x plus c. The intercept c is found just by taking one of the points and subbing it into this equation and solving for c. So for example, we could take 2, 1, sub x is 2 and y is 1 in there, and solve for c to get c is minus 1. Alternatively, we could take the other point, 3, 2, and say using 3, 2, we would have 2 is equal to 3 plus c, and again, c is minus 1. Alright, which gives us y equals x minus 1, just as we got using the other point. Now if we want to find an angle, theta, from the positive end of the x-axis, well, tan theta is the slope, right? So in general, tan theta is equal to m, the slope. But here our slope is 1, so we have tan theta as 1. Taking the inverse tangent, we have theta as arctan of 1, that's 45 degrees, or pi on 4 radians. Alright, so let's have a look at some of these pictures here. So if we have a slope that looks something like this, or this, or this, or this, that's a positive slope. Whereas if it goes this way, something like this, that's a negative slope. So as x goes from left to right, the value of y is decreasing in a negative slope. Okay, if m is equal to 0, then that's a horizontal line. Now, if we have a vertical line, then the slope is not defined. But you can still represent the line. Okay, take for example the vertical line that's parallel to the y-axis, say, so e.g. x equals 3. Okay, this is a vertical line. Now notice y is missing in its equation, right? Because remember, we have y equals mx plus c, but here we have got x equals 3. So y is actually missing in that. That is telling you that the line is vertical. Okay, so the general equation of a straight line is y equals mx plus c. Now there's also a way that you can write this with vectors. So the m corresponds to going 1 unit this way and m units this way. Okay, so as a vector, that vector to go 1 unit that way and m units this way would be the vector 1 comma m. And then I could write r equals the vector 1m multiplied by some parameter t, and then plus some point that I already have that's on the line. Let's say p0. Now this gives you a description of points for any real choice of t. It just gives you another way to represent that line in terms of vectors. So let's have a look at some examples here in figure 37. On the left we have the line y equals 1/2 x plus 2, and on the right we have the line y equals minus x plus 5. So just out of interest, I'll give you the vector equations of these lines. So we've got vectors parallel to this line are given by v equals 1 and then m. Okay, and now do I have a point on the line? It looks like yes, the point 0, 2 is on the line. And so I can write the vector equation of the line like this, where t is any real number. Okay, now what this means is that if I choose a real number, I get a vector from, now this is from O to x, where x is, say, xy, the point xy, and O is the origin. Okay, so take t equal to, let's just choose 2 for example. Right, so e.g. take t is 2, what do we get? We get OX is, now 2 times this is the vector 2, 1 plus 0, 2, and so we get 2, 3. Okay, now that's from O to x, so this is OX, which is the point x minus the point O. So this gives us the coordinates xy of a point on our line. Let's just check. 2, 3, yes. 2, 3 is on the line. Alright, but I would get a point on the line for any choice of real t. Now similarly, we could do the same for this. So in this case, m is minus 1, and we've got an easy point to choose. We could choose any point. How about 0, 5 is a point on that line. So if I wanted to write this in vector form, then I just say 1m, so 1 minus 1 times t plus p0, any point that I know is on that line. Okay, and now if I choose, let's just say e.g. choose t equals 3, for example, then we get, because we can write OX as x minus O, we have xy is 3 comma minus 3 plus 0, 5. And we get the point 3, 2 when we add those up. Okay, is that on this? So yes, it's right here. So you see that works nicely. So this is what we call the scalar equation of the line, and what I've just shown you are the vector equations of those respective lines. All right, next topic, linear interpolation. The purpose of the exercises in this section is to predict values for the data that we do not have a measurement for. So if you're looking at this picture, right, you might see there is a bit of a trend. Looks like a parabolic trend, like a ball being thrown up, and so it goes up and then it comes down, right? So this is time, this is displacement, but you know that when you throw a ball up, you do get a nice smooth curve, right? You don't get these little bumpiness. So that would be errors in the measurement of the displacement. Okay, but interpolation is all about finding the values in between where we don't have measurements. And it's a pretty primitive method, and so if you read on ahead, there's a much better method than this called the method of least squares, and like I said earlier, I won't cover that today. I'll just let you read through that. It's pretty straightforward and not much of a leap beyond this. Alright, so for example, suppose we have a series of measurements of displacement at various times. See the figure. Displacement is a vector. However, we assume for this example that this is one-dimensional. We aim to predict the displacement when t is 1/2 second, or 1.25 or 2.75 seconds, for example. In other words, between the measurement values that we have. If the points we predict are within the minimum and maximum x coordinates, or t coordinates in this case, the independent variable of the data set, then we say interpolation. Otherwise, the predicted process is called extrapolation. So that would be to use the model outside of the domain for which we've collected data. We'll focus on interpolation using linear methods here. Okay, so example 12.1. Consider the experimental data. Now, is this... No, it doesn't quite look like it corresponds to this diagram, so it's different. Okay, so we've got some data here. T is time in minutes, temperature of something in degrees C at various times. So what is an estimate for t equals 4.2 minutes using linear interpolation? What's an estimate for 1.6 minutes using linear interpolation? Okay, where are these numbers in the time? So 4.2 is between 4 and 5, right? So we would expect then that the corresponding temperature at 4.2 would be somewhere in between 18 and 25 degrees C. Alright, now for 1.6 minutes, it's between 1 and 2, so we might expect the temperature to be between 12 and 15 degrees C. Alright, so here we've got a plot, and then this is at 4.2, it looks like roughly, so we might expect this to be about 20 degrees C. So we could plot the points, all of those points that were given in the table, this table right here, and estimate the temperature at 4.2, see the figure. Using the method, it would seem that the temperature at 4.2 should be approximately 20 degrees, but we can do a little bit better. Using interpolation, we take the points on either side, so the 4.0, 18 and the 5.025, and since 4.2 is between 4 and 5, we calculate the slope of the line segment connecting those 2 points. However, this method doesn't take into account all of this other data here, right? So, for example, the problem with this is this could be way down here, could be a sort of an anomaly reading, right? And you'd get a bad estimate for that, right? But So like I say, it's a fairly primitive method, and a better method would be the method of least squares, because that would take into account every data point that you had. Anyhow, okay, so what we do is we take the slope between these 2 points, you know, the slope from here to here, and so let's draw on that. It gives us a slope of 7 from this calculation right here. So then what we do is we let our new point that we're interested in be the point 4.2 t. That's the predicted point, and we take this equation and we simply solve for t, right? Because remember, the slope is y2 minus y1 over x2 minus x1, and since we know that that should be about 7, we can take this and solve this for t. Okay, now notice that we've taken 418, so that's on the left, right? So we keep the order the same. So this we're calling our x1, y1, and then this one in that calculation we're calling x2, y2, right? So I'll label that here, x1, y1, and then this x2, y2 in the final part of the calculation to find, and this incidentally is our t, to find t. Okay, so we solve this linear equation for t. So this denominator is 0.2, so we've got 7 times 0.2, and then we take the 18 over to the other side, and we see that t is 18 plus 0.2 times 7, and this is 18 plus 1.4, which is 19.4 degrees C. Now we would get the same result if we instead used the point on the right, the 525, as our x2, and this one here as our x1, right? So you can choose, which is nice. You should get the same result. Okay, but here we get t is equal to 13.8 degrees. Where is that for the second one? Ah, yeah, sorry, this is the second one. Okay, let's have a look at the second point. So what's this say? Note that if we instead used 5, 25, we get the same result. Okay, so now at the bottom here it says to predict the temperature when t is 1.6 minutes, we use the same approach, but the points on the either side of 1.5 t are 1.012 and 2.015. We take the slope of these two, or the slope of the line segment connecting those 2 points. We have a slope of 3. So again, we do the same technique, put 3 equals t minus 12 over 1.6 minus 1 and solve for t, and this time we get 13.8 degrees. For the temperature of that point at time 1.5 minutes. So like I said earlier, this approach has some pretty severe limitations. That being that it only takes into account the 2 neighbors on either side. And a much better method would be to use least squares, so that you take in all of that information and the effect of some outliers are minimized then. Alright, let's move on to our next topic, logarithms and exponentials. Suppose we want to solve the equation x to the 4th is equal to 18. The fundamental theorem of algebra says that there are 4 solutions. Alright, so that's if we include all repeated roots in that count, and we include complex numbers in that count. Okay, so let's have a look at this example. Suppose we want to solve the equation x to the fourth is 18. The fundamental theorem says that there are 4 solutions including repeated roots and complex numbers. So first, we could write it this way and say that this is x to the fourth minus 18 equals 0. So just taking the 18 over to the left-hand side, and then we can view this as a difference of 2 squares, right? So 18 is root 18 squared. So then we have x to the fourth minus 18 is, in brackets, x squared plus root 18 times x squared minus root 18. But notice 18 is 9 times 2, so these are 3 root 2. But we can factor x squared plus root 18 into a product of 2 linear complex factors, but we cannot factor that over the real numbers because we require complex numbers that are not real in order to get its linear factorization. Alright, now x squared minus root 18 can also be viewed as the difference of 2 squares and further factorized. So our complete real factorization is x squared plus root 18 times x plus the fourth root of 18 times x minus the fourth root of 18. So we get 2 real solutions from these two. So plus or minus the fourth root of 18, which is approximately 2.06. But there are 4 complex roots because you can factor this into the product of 2 linear complex roots, or complex factors. Okay, so possibly a more familiar approach would be just to take the fourth root of both sides. So if you did that, you would immediately get x is the fourth root of 18, which is approximately 2.06. And you can just plug into the calculator to do that, but you only get one answer, right? So you have to use your brain to think about what the other possible answers are. So next let's have a look at the equation 4 to the power of x is equal to 18. Now solving for x in this case requires the inverse function to exponentiation, and that's called a logarithm. We apply log to base 4 of that equation there, and so we get x is equal to log to base 4 of 4 to the power of x. Now there's a log rule that says I can pull this x down, but also a log to base 4 of 4 to the power of x asks the question, what power do I have to raise 4 to in order to get 4 to the power of x? Well, obviously it's that x there, right? Okay, so x is equal to log to base 4 of 18. Now there's a rule that says we can change the base. We can insert our own favorite base so that we can easily solve this on the calculator. Alright, so if we decided to do this in terms of base e, then the change of base log rule would say that log to base 4 of 18 is log to base e of 18 divided by log to base e of 4. In other words, natural log of 18 divided by natural log of 4. Some people refer to this as ln. Okay, if you wanted to use base 10, then you could say that this is log to base 10 of 18 over log to base 10 of 4. And so both will give the same answer, approximately 2.085. And so in case you didn't know, e is the base of the natural logarithm. So Leonhard Euler made the most use of this number in his mathematical writings. So I assume that e is after Leonhard Euler, but it's also known as the Napier logarithm. or the base of the Napier logarithm, that is. And this is defined by a limit of a certain sequence. Okay, logarithms are equivalent to expressions of powers. So let's have a look at this diagram from Dr. Lauren. 10 to the power of 3 is 10,000, so the base here is 10 and the exponent is 3. So what she's saying here with the 3 horizontal lines is this is defined as, or the 3 is defined as, or this is equivalent to, okay? Log the base 10 of 1,000, which is equal to 3. Oh, hang on, I see, Lauren. Okay, so what you're doing there is you're saying that this is logically equivalent to. So this equation is logically equivalent to this equation. So let's put some big brackets around it, if that's what's meant here. Right, so these equations, this one implies this, and this equation implies this. Okay. But sure, there's also a definition of the logarithm that comes from this. If 10 to the power of x is 100, then clearly x is 2, but we can solve that through the logarithm because an equivalent equation is log the base 10 of 10 to the power of x is equal to x. And then you can calculate that in the calculator and put in 100 and log the base 10 of that, and you can get 2 telling you that 10 to the power of 2 is 100. Okay, example 12.2. Solve the equation 10 to the power of x is 105. Now, applying log to base 10, because we have a base 10 there, to solve for x, equivalently, x is equal to log to base 10 of 105. Now this goes into the calculator directly, and you would get 2.2, 2.0211, and so on, right? Approximately. Okay, example 12.3. Use logarithms to write 1500 to the power of 50 in scientific notation. Now that's a typo there. It should say even though this number overflows the memory of a typical hand calculator. Yeah, that would definitely overflow the memory. Okay, so let's let uppercase N be 1500 to the power of 50. Applying log to base 10 of both sides, we have log to base 10 of n is log to base 10 of 1500 to the power of 50. Now a log rule says that we can bring this 50 out the front and say that it's 50 times log to base 10 of 1500. So this is approximately 50 times 3.17 or so, which gives us 158.805. Okay, now back to what n is. So what we've just done is worked out that n is equal to 10 to the power of 158.805. Okay, now we want to pull out the integer part of this, separate this as a sum of the greatest integer, which would be the floor of this number, 158 plus 0.805 and so on. And then separate this using an exponent rule. So in other words, a to the power of b times a to the power of c is equal to a to the power of b plus c. Right? So we're using this in reverse. So we have 10 to the power of 0.8 times 10 to the power of 158. So 10 to the power of 0.805 is approximately 6.38. So we can say that n is approximately 6.38 times 10 to the power of 158. And put this in scientific notation, giving an estimate for it. in so many significant figures, even though if we tried to put this number into the calculator, we would just get some kind of error because it overflowed the memory. So that's a big number. There are approximately 10 to the 80th atoms in the observable universe. And the observable universe would be, you know, that part, 13 point whatever billion years distant, that we are able to see due to the speed of light. Alright, now this is an important page right here because it just lists all of the relevant log rules that you might use. So let's go over these carefully here. So the first one says that the log of a sum, or the log of a product is the sum of the logs, okay? The sum of the logs, provided they have the same base, is the log in the same base of the product. So this one is directly related to this one because in this product you can write x over y as x times y to the power of minus 1, right, and use this log rule together with this log rule to get this log rule. Alright, so this one says we can pull down these powers and put them in front. That's pretty handy. Log to base a of 1 is 0, so in other words, a to the power of 0 is 1. This one, again, pulling down the power, so using this log rule here, we pull down the power, then log to base a of a is 1. So that's x times 1. This is essentially coming from the definition of a log. So a to the power of log to base a of x is x. And this one here is the change of base rule. So we can put in our own favorite base c. Now usually we would want to choose e or 10 for that. But sometimes we want to choose another number that happens to be involved in the a and the b, to simplify that. Alright, now what we've got here in figure 40 is a plot of the log function. Now if you turned it the other way and called this the x-axis and this the y-axis, then you would see an exponential increase going this way. So this is the inverse function of e to the power of x, right? And otherwise you could just reflect this about the line y equals x. If you reflected that about the line y equals x, you would also get a plot of the exponential function because log to base e of x, or ln of x, is the inverse function of f of x is e to the x. Okay, so here we have the definition of e, and it's a fairly important number in mathematics. So here's its definition. So if you have a sequence starting with 1 plus 1 over 1 all to the power of 1, so in other words you get 2, okay, that would be the first term. And then your next term of the sequence is 1 plus 1 over 2 all to the power of 2. I think this is on the next page. Here we go. So 1 plus 1 over 2 to the power of 2 is 1.5 to the power of 2, which is 2.25. And so if you kept that pattern going, you get these numbers. But as they go on, they get closer and closer to the number e. All right, now there are other ways to calculate e. For example, this way to calculate e, I believe, is a bit better than calculating e in this way, right? Because I think this is slow to converge, whereas I believe that this is faster to converge. Now note that 0 factorial is defined to be equal to 1, just as 0 to the power of 0 is defined to be 1. Now, an important property of e is that the slope of the curve y equals e to the x is e to the x at the point xy. Alright, so in other words, if f of x is equal to e to the x, then the first derivative f dash x is also e to the x, if you've done calculus. Alright, let's have a look at some other properties. So E governs exponential growth in nature, such as population growth, compound interest, carbon dating, half-life, probability theory. For example, in the probability density function, here's E and pi. So E and pi are very, very important numbers in mathematics. It's related to the sine and cosine via the complex number formula. So e to the power of ix, where I is the square root of minus 1, is cos x plus I sine x. Okay, so back to logarithms. Natural log is also ln of x. It's the inverse function of e to the power of x. Conversely, the exponential function is the inverse function of the natural log. So let's have a look now at these examples. Solve ln of p is 6.31 for p. Well, that's easy. Okay, so we just write this in the exponential form. So that says p is equal to e to the power of 6.31, and that's approximately 550.05. Next example. Solve log to base 10 of m squared for equals 0.32 for m. Okay, so remember we can bring down that power of 2. So we've got 2 log to base 10 of m is 0.32. Now we could divide by 2 and say that log to base 10 of m is 0.16. And then m is equal to plus or minus 10 to the power of 0.16. Now, why the plus or minus? Well, because we had a square there, right? So inside that square, if we put either the plus or the minus, squaring that would give a positive number. So there are two solutions to that. Alternatively, m squared is 10 to the power of 0.32, which is approximately 2.09, and again, taking square roots gives you plus or minus 1.44544, and so on. Example 12.6. Solve e to the power of 3x plus 2 is equal to 10 to the power of x minus 1 for x. Okay, on the left we have an e, on the right we have a 10. So we can choose base, but if we chose the natural log of both sides to take, then we would have the exponent 3x plus 2 equals log to base e of 10 to the power of x minus 1. Now remember, we can pull down that exponent that is inside the log, and so this is x minus 1 times log to base e of 10. We can easily calculate that on the calculator. Okay, but we want to solve for x here. So let's see, you could expand the right hand side and then collect the like terms, taking the x's with the x's and the single numbers with the single numbers, and get 3 minus log to base e, or natural log of 10, all times x equals minus 2 minus natural log of 10. And then you divide by this and you have your solution for x. So that gives us x is equal to minus 2 minus natural log of 10 all over 3 minus natural log of 10, and this is approximately minus 6.169. Okay, so that's fairly straightforward. Now I said I wasn't going to cover least squares. It's not examinable this year. But it's really an interesting way and a better way to get a model for just a collection of data like this than interpolation or extrapolation is, because the outliers are not so seriously affecting your prediction in there. It takes in all of the data and gives you a best fit. However, it does involve a little bit of calculus, so I'll show you what I mean, and I really hope you do read through this. Alright, so the part that involves calculus here is just this gradient vector. Alright, so the gradient vector is, so let's just write grad f is equal to the partial derivative of f with respect to x, comma, partial derivative of f with respect to y. Alright, so you need to know calculus to be able to calculate these. But this is a derivative in the direction of a particular variable, right, or parallel to the x-axis, or the y-axis, right? And it's a vector. Called the gradient vector. Okay, and in particular, gradient vector at xy is the zero vector when f xy is least or greatest, right? And so this process involves minimizing the sum of the squares of the distances to some generic line that you're assuming is the best fit to the entire data set. Okay, and then the rest of it just comes down to some pretty simple calculations. But again, I won't go over this. I'll just let you read it if you want to get better at mathematics. Okay, but you can see it does involve quite a lot of linear algebra there. All right, thank you.